Welcome to this Masterclass Explainer, everyone. Today, we're dissecting algorithmic design patterns, specifically the absolute allure and the inherent danger of greedy algorithms. We're going to look closely at how algorithms make decisions under pressure, when prioritizing immediate gratification actually pays off, and, well, when it leads you entirely astray. Here's our syllabus for today. We're covering the greedy mindset, activity selection, optimal substructure, greedy versus dynamic programming, and finally, when greed fails. Section 1. The greedy mindset, chasing the local optimum. Okay, let's dive into this core concept. A greedy algorithm is essentially designed for optimization problems. It always makes the choice that looks best at the exact moment it's making it. It's making a locally optimal choice in the hope, and definitely notice that word hope, that this choice is naturally going to lead to a globally optimal solution. It's kind of like a student picking the easiest homework assignment first just to get it out of the way. They make the local choice, hoping it naturally builds into a perfectly productive study session. It acts as a really fantastic heuristic, a great rule of thumb. But I want you to really ask yourselves as we get into the weeds here, does prioritizing immediate gratification actually guarantee the best final outcome, or is it just a handy shortcut? Because the truth is, greed doesn't always yield the optimal solution. In fact, sometimes it behaves very, very badly. Section 2. Activity selection. Mastering interval scheduling. Let's put our hypothesis to the test with a classic real-world scenario. Imagine you manage a single lecture hall and you got multiple groups desperately wanting to use it. The goal is to fit the maximum size subset of mutually compatible activities into our schedule using a greedy strategy. And mutually compatible just means the start time of one activity happens after the finish time of the previous one. Literally no overlapping allowed. Now, the real trick to this setup is how we prep the data. We have 11 activities here, and they are carefully sorted by their finish times, from earliest to latest. Activity 1 finishes at time 4, Activity 2 finishes at time 5, all the way down to Activity 11 finishing at time 16. Sorting them in monotonically increasing order of finish time is absolutely crucial. It's step 1 for our greedy algorithm. If we walk through the recursive activity selector steps, the greedy choice is almost laughably simple. Just pick the activity that finishes first. By choosing Activity 1, which ends at time 4, we confidently make a choice that leaves the maximum possible room for all the remaining subproblems. We then just look for the next activity that starts after time 4, select it, and recurse. It's fast, it's incredibly efficient, and for this specific interval scheduling problem, it actually guarantees a mathematically optimal schedule. Section 3. Optimal substructure, the science of greed. Now, we can't just rely on intuition in computer science, right? How do we prove this works? Take note of this 6-point checklist. To responsibly deploy a greedy strategy, you fundamentally have to prove the problem has what we call optimal substructure, meaning the global solution absolutely contains optimal sub-solutions. You must prove that making the greedy choice is safe, meaning it definitely belongs to some optimal solution, and verify that making this choice leaves exactly one solvable subproblem. Once you nail that proof, you can confidently write out your recursive algorithm and then ultimately convert it into a blazing fast iterative one. Section 4. Greedy versus DP, the heavyweight bout. Because let's face it, greed isn't the only game in town. Let's pit it against its brilliant, notoriously rigorous rival, dynamic programming. The visual contrast here is stark. Greedy algorithms just charge ahead, top-down. The current choice is based strictly on local information, and the highest level choice is made before any subproblem has even been solved. It's bold. Dynamic programming, on the other hand, strategically builds bottom-up. In DP, the subproblems get solved first. The algorithm systematically builds upon those smaller solutions, reusing them to solve increasingly larger subproblems until the original top-level choice is finally made. Section 5. When greed fails. The knapsack problem. All right, here's the twist in our explainer. When does this top-down greedy arrogance completely backfire? Let's talk about the famous knapsack problem. Imagine you're packing a knapsack with a strict 50-kilogram weight limit. You've got several really valuable items, but in the 0-1 knapsack problem, you must take the whole item or leave it behind entirely. No breaking items apart. You either select the whole thing, a 1, or leave it at 0. And your objective is to maximize the total volume in your bag. Now, alternatively, we have the fractional knapsack problem. The weight limit and the goal are exactly the same, but imagine instead of solid, unbreakable items, you're packing something like gold dust or flour. In this version, you are allowed to take fractions of an item to perfectly top off your bag. Let's look at a specific data set to see this in action. We've got 3 items at our 50 kilogram limit. Item 1 is 10 kilos and worth $60, which gives it the highest value per kilo at $6 a kilo. Item 2 is 20 kilos, worth $100, so $5 a kilo. And item 3 is a massive 30 kilos, worth $120, putting it at only $4 a kilo. So if we unleash a greedy algorithm onto the 0-1 knapsack problem, what exactly happens? Well, it blindly makes the locally optimal choice. It sees item 1 is worth $6 per kilo, the highest rate, so it grabs it. Then it sees item 2 is $5 per kilo, so it grabs that too. Now our bag has 30 kilos in it and we've made $160. But look at the problem we've created. We only have 20 kilos of space left. We literally cannot fit item 3, which weighs 30 kilos. This perfectly illustrates the failure of greed. The algorithm just stops, maxing out the bag at a highly suboptimal $160 and leaving 20 kilos of totally wasted space. But hold on, watch what happens when we apply dynamic programming instead. If we had analyzed the whole picture bottom up, meticulously evaluating all the subproblems, we would have seen that completely skipping item 1 allows us to take both item 2 and item 3. 20 kilos plus 30 kilos perfectly fills that 50 kilogram limit, yielding a massive $220. This mathematically proves that for the 0-1 knapsack problem, a top-down greedy strategy just fails completely. You absolutely need the bottom-up rigor of dynamic programming to lock in that optimal combination. However, let's look at what happens if we switch the rules back to the fractional knapsack problem. Grabbing the highest value per kilo first actually works flawlessly here. The greedy algorithm takes all of item 1, all of item 2, and then, because we can take fractions, it takes exactly 2/3 of item 3 to perfectly fill the remaining 20 kilos of space. Because we don't waste a single ounce of empty space, the greedy method perfectly maxes out at $240. So when the rules allow fractions, the greedy rule of thumb is an absolute winner. Which leaves us with a final thought for today's explainer. As you design systems, schedule your time, or allocate your own resources, you have to ask yourself, when analyzing your own systemic problems, is a fast, top-down greedy rule of thumb enough to get the job done? Or is there hidden complexity? Must you demand the rigorous bottom-up precision of dynamic programming to find the true optimal solution? Understanding the mathematical boundaries of greed is the very first step to mastering it. Thank you for joining this masterclass.